Okay, so I thought for this accessory video, what I could do was show you guys how how I basically remember the activities that we need at the replication forks in the genome. So I find that it's very helpful to draw out the process of trying to replicate 2 strands of parental DNA. And just from drawing and thinking about it, we can actually derive most of the activities that we're going to need in the replication fork in order for the process to be able to go. And I think for me anyways, that makes it a lot easier to remember the different the different things like the helicases and the primases and stuff, because in my mind I know exactly why those activities are needed. And I think that again, building a map in your mind of what's happening in this process is going to be helpful for learning the material. And so let's go ahead and draw and derive a replication fork together. Okay, so if we were to imagine what we need to do to replicate our genome, well, we were starting with 2 strands of double-stranded DNA. And in order to copy each strand, we're going to have to separate those strands from one another. Okay? And so let's say that this was 5' to 3'. So if we were to separate this, it's 5' to 3', 3', 5'. So if we draw our ends like this, already we know that to pull these strands apart, requires energy, and so we're going to need some activity to help us do that, and those activities are provided by helicases. So their function is to unwind these strands. Okay, now once we've unwound the strands, we can start doing synthesis, and we know that for each of these strands, the direction of the complementary strand synthesis is going to be in this direction for the bottom strand, 5' to 3', and it's going to be this direction, 5' to 3', on the top strand. But in order for polymerase to be able to do anything, we know that a primer is needed on which to begin the synthesis. And so right away we can say, well, we're going to need to place some sort of primer sequence at the that makes some interactions here with our strand here, and those are going to have a 5' to 3', 5' to 3' geometry. Because if these primers aren't there, nothing's going to happen. The polymerase isn't going to be able to do anything. So we need to add primers, and that's done by an enzyme called primase. Okay, and once these primers have been added, it is now straightforward for DNA polymerase to go ahead and synthesize more complementary strand here, and same thing over here on this strand. Okay, and so far so good. So this is DNA polymerase, and unfortunately one thing you do have to memorize is that this main polymerase activity is performed by Pol 3. But so far everything's just kind of a natural deduction, right? We needed to unwind the strands. That gave us single-stranded DNA, but because DNA polymerase requires a primer to extend, we knew we needed to have an enzyme that could put primers on there, and that's what primase does. And then polymerase can go in and fill on and so forth. But let's remember that in terms of this unwinding, we're going to continue unwinding our genome. And so this replication fork is going to continue to move in this direction. And so let's see what happens if we unwind this strand a little further, and we'll look at where we are and what that means for what has to happen next. So what's going to happen if this is where we're currently at and we keep unwinding in this direction. That is, our replication fork continues to move this way. So let's leave the amount of synthesis we've done as is, and let's just further unwind the bubble, or unwind the fork, and see what it means for what happens next. So let's say we unwind some more of this sequence here. And again, always label your end so you know what's happening. 5' to 3', 3' to 5'. And so we had our primer here, and we had our primer here, and then we had our Pol 3 catalyzed extension here. Okay, and let's just label our ends again so we keep everything 5', 3', 5', 3'. So after a little bit more unwinding, this is where we find ourselves, right? And let's ask what happens if, for Pol 3, if it wants to keep adding on. Well, on this top strand here, 5' to 3' means that our polymerase here can just keep extending, right? Can keep moving on in the 5' to 3' direction, making the complementary strands. However, if we want to add to this region here, well, unfortunately, as we've discussed many times, polymerases can't add to the 5' end. They can only add 5' to 3'. And so essentially, if we keep unwinding in this direction, in order to add sequence here, we're going to actually have to add a new primer and extend from there. Otherwise, there's no way to add anything to this region here. And so what this means is, at this end, we're going to have no choice but to add another primer, right? Because otherwise, how are we going to make this DNA? It has to go 5' to 3', right? And so in order to synthesize this bottom strand, we have no choice but to put this primer down, and then we can extend up until we reach the other primer here, okay? And so right away, just by drawing it out, we automatically can deduce that there's going to be a leading strand which can undergo continuous synthesis in the direction that the replication fork is moving. And then there's going to be what's called a lagging strand, which is basically going to be a discontinuous synthesis in this direction. So we're going to make fragments of this bottom strand here. Okay, and so we didn't need to memorize that. We could just draw the picture, and it's obvious that this is what's going to have to happen. And once we realize that there is a lagging strand, it becomes obvious that a few additional activities are going to be needed to successfully replicate the lagging strand. And so let's think a little bit more specifically now about the lagging strand. So if the lagging strand here, we are making fragments that are made up of primers here, and Pol 3 synthesized extension off of these. And so for each one of these, I'll just jot down that we're looking at the lagging strand here, 5', 3', 5' to 3'. So this is what we're producing, are these chains of Okazaki fragments, they're called. But it's more important, you don't need to know the guy's name. I mean, you should know the guy's name, but it's more important to realize that you're making these fragments. And then this should make it obvious to us, because primase, it turns out these primers here are RNA. And secondly, we've got these discontinuities here. And so if we draw this picture, then we know that we're going to need two additional things to deal with the lagging strand. And that is, we're going to need something that's going to replace the RNA with DNA. And we're going to also need something that can connect the fragments together, right? So if we just think about lagging strand synthesis, we automatically know that we need somebody to replace, get this RNA out of here, okay, replace it with DNA. And then what are we going to do about these discontinuities? Somebody's going to have to come in here and connect those things together. And so once we know that those activities have to exist, it's not too hard to commit to memory, for example, that it's going to be the activity of a polymerase called Pol1 to do this activity. And the connecting the fragments together is performed by an enzyme called DNA ligase, because ligation is the process of connecting two pieces together. And so again, by simply thinking about the process that's going on, it's very straightforward to recognize the additional activities that are needed. And so what I would say about having to learn these replication fork activities is that I think this strategy of basically when in doubt, draw it out is really the best way to not only learn the material, but actually really understand what's going on. And so I would highly recommend you do these for yourself, where you just start with the double-stranded DNA and realize that to replicate it, you're going to need to unwind it. And that's where the helicase activity comes in. And then if you draw this out, you'll realize that you need primers on your 5' or your ends here to be able to extend off of for polymerase. And so the need to prime creates a requirement for primase. And then if you keep opening your replication fork and unwinding it, you'll realize that to synthesize this stretch right here, you're going to need another primer to extend off of, whereas this strand's going to go continuously. And so just by drawing it out, we realize that there's going to be this leading strand and this lagging strand. And to deal with this situation of what we're creating here, we're going to need additional activities to remove the RNA, and that's provided by Pol1. And we're going to need a way of sealing all these fragments that are generated on the lagging strand, and that's going to be done by DNA ligase. But if you were to just keep iterating on those processes, then of course you would be able to copy, use the parental strand in black to make a copy daughter strand in orange here, and that basically gives us the semi-conservative replication that we've been talking about, and that's pretty much, you know, the main thing. And so yeah, I mean, you of course can memorize things however you see fit, but this is the easiest way in my mind to lock down not only all the components that go in, but also to really understand the process, because basically each one of these activities is a solution to a problem that comes from trying to do this semi-conservative replication.